Hello everyone, welcome back to our data structures and algorithms concept series. We'll cover a stack data structure today. We'll understand what exactly is stack data structure using some real life examples. We'll also try to understand the implementation of stack in different modern programming languages, libraries, different use cases where stack is used, and the performance of different data operations using stack data structure. So by the end of this video, we'll get some basic idea or our concept will be clear about when we should use the stack data structure and what are the scenarios where stack data structure will be beneficial to use in algorithms. So let's start. Let's understand the stack using real life example. When you go to the cafeteria, right, what you see basically, you see a stack of plates and you pick up the top plate from that stack and take a food, and when you remove the top plate, the plate below it becomes the new top, right? Now if suppose the new plate is added to the top, then that new plate will be basically the top plate, right? Now whoever comes after you will pick up the new plate from that stack because that is the top of the stack now, right? So if we see, the last plate which is added to the stack will be the first plate removed by anyone who is coming to the cafeteria, right? Now let's understand with one more example. Let's say here from main method we are calling method A, from method A we are calling method B, from method B we are calling method C, and in method C we are just printing, right? Now here we are calling a nested function calls, right? Now in this nested function calls, after the method C is finished, it should come to method B, and then once the method B finishes, it should come to method A, and from method A it should come to main method, and program should exit. Now how is this handled? Basically our operating system have a uh, uh, tracks the function execution order using the call stack. This is internally implemented on a operating system side. So it uses a stack like data structure. So for example, if you see, it will put the method A to the stack, and then method B, the top pointer is changed, then method C, then the top pointer is pointing to method C. And once the method C finishes, the call will return to method B, finish the execution in method B, and then the call will come to method A, finish the execution in method A, and then the program will exit, right? So based on the previous two examples, what we understand is that stack is a linear data structure. So each element is connected to only the one element, basically the next element, right? So it's a linear data structure, and it follows the last in first out principle. So this means that whatever the last item added is the first one to be removed, just like the stack of plates in cafeteria, where the last plate which is added to the stack gets removed by the any student coming to the cafeteria first, right? Or the function calls on a call stack, the nested function calls which we saw in a previous example, right? Now let's understand the stack implementation. So if you see, most of the modern programming languages, right, they provide a inbuilt stack support. They provide the inbuilt library support for a stack data structure. Internally, which is not exposed to us by the way, internally stack is implemented using dynamic array or a linked list, right? But to us, when we use the stack data structure using the inbuilt library, only the methods which are relevant to the stack data structure are exposed, like pushing the element to the top, removing the element from the top, or getting the top element, or whether stack is empty or full. Only such methods are exposed, right? Other capabilities of arrays and linked list are not exposed to the library, inbuilt library through which we use the stack in our program, right? Uh, for languages like C, which does not provide a inbuilt support, uh, we can still implement it using a static array, right? So it will be like a fixed array you can declare, and we can have the custom logic to have a stack-like functionality, right? Let's understand the stack implementation using array, right? So let's say we have the array of size 5, and we will maintain the top pointer. It is -1 initially because there is no element onto the stack. If we push the element to the stack, you can see that the top is pointing to the position where last element is inserted, right? So now we keep on pushing, and once it reaches to the capacity of the array, it is says stack is full. Now in case of static array, we will not be able to add anything, but in case of dynamic array, the resizing happens internally, right? Dynamic array resizing, how the resizing happens, you can check out the array data structure related video in our series. That will give you more idea about this concept, right? And one similar to push, basically when we try to remove or pop the element, then you can see the top is decrementing, and coming to once it comes to the -1, it says that stack is empty and we will not be allowed to pop any item because there are no items left, right? Now similar stack we can implement using the linked list as well. In this, but in a linked list, it is not predefined size, right? It is a reference, right? So you will create one class called node int value. Now value type can be int, gas, string, whatever you want to. And then node next basically contains the reference to the next element on a stack, right? So if we see, top will be pointing to null pointer. If we push 5, then it creates a new object and top stores the reference of that object. Now next is null because there is only one element. Now when we push 7, now the top becomes 7, and the next becomes the reference to the node 5, which is the previous element, right? The element below the top, right? And if we push, let's say 10, then the top refers to the 10 memory of the 10 node object, that node object with the 10 value, and the next refers to the 7, the reference to the node with the 7 value, right? And when we pop, then the top goes to the next value of 10, which is the reference to the node 7, right? Now the top contains the reference of the node 7, and the next of that is reference to the node 5, right? Now if we remove the 7 also, then the top will come back to the next of 7, which is reference to the node 5, right? And the next will become null, right? So using this in this way, in this case, right, using a linked list, there is no predefined memory assigned, or there is no resizing happening. It actually uses creates the object whenever required, but it has some of the like at disadvantages, like it will require more memory because it needs to maintain the next object reference, right? And it is a memory reference, so it will have to it will be slow because it is a random memory reference, right? It is not something contiguous memory block like array, right? So it will be random memory reference, so it will be slow compared to array. That is why, and there are a few more reasons. So that is why most of the programming language which provide the inbuilt stack support internally implements the stack using array, right? Now coming to the use cases, right? So when should we use the stack, right? Or basically, what are the use cases where stack is used today, right? So whenever we need to keep a track of operations, right? For example, let's say you're doing step 1, step 2, step 3, step 4, and there is a requirement that you need to come back to previous steps also, right? So for example, when we took the example of function calls, right, we call method, the nested functions called method A, method B, method C, and from method C there was a requirement to come to method B, and there was a requirement to come to method A, right? So now if we don't keep a track of it, and the we need to return back to the previous last operation, in such cases the stack can be used, right? Now for some of the examples, let's say when you type undo redo functionality in your text editor, right? So let's say you write some code like int val in a program, right? But you say that no, I don't want to give the name of the variable val, I will give maybe value, right? Or maybe int variable, something like that. Then what you do, basically you just do control Z, right? And that val will be removed, only int, and then you type the new variable name, right? It means that it provides you that. How is this provided? Because whatever you are typing, right, that last action is stored onto the stack, and when you do Control Z, that last action will be removed, right? And similar to, and one more example which we understood in a previous slides, right? The function call stack, like method A, the nested function calls method A, B, C, which we understood, right? So these are some of the examples where this keeping track of operations is required. So that is why the stack is used in such cases, right? One more very generic use case is that when you want to do the processing of the data in a nested fashion. For example, you might have seen that our compiler uh, uh, compiles the code, right? And if there is any syntax error, let's say you forgot to add one parenthesis, it will give an error. How does it check? It uses the stack only for this purpose. So it will basically use the stack where it will keep on putting the opening brackets, and once it sees that this close bracket, then it will check the top whether it is matching the bracket type, it will remove. Then when it sees the next closing bracket, then it will basically remove that from the stack and go on further. And now the stack is empty, means it is valid. We saw two opening brackets and two closing brackets here. That's why for any opening brackets were pushed to the stack, and whenever the close bracket was encountered, it was removed. The opening bracket was removed from the stack, right? And if the number of opening and closing brackets are same, then the stack will be empty. It means valid, right? And one more use case is expression evaluation. For example, let's say 3 plus 4 into 5. So the answer for this is 23, right? How does it, how is this evaluated? So internally it uses the stack only. So it pushes the stack, there will be, it uses a stack, two stacks, one a stack A and stack B. Stack A is for numbers, stack B is for operators, right? So it will parse, it will put plus there, it will put 4 here, it will put uh, multiplication here, it will put 5. Once the processing is done, it will remove the 4 and 5 from the stack A, which are operands, and remove the star from stack B, which is basically the operator, and it will compute the result and push to the stack A, right? Now again it will pop the 20 and 3 from the stack A, and plus from the stack B, perform the addition and push the 23 to stack A. Now the result is 23. So this is very simple example expression evaluation. There are a lot of complex example also, but you can see that you have to process this expression evaluation in a nested fashion, right? So here, this is also use case where stack is used, right? So depending on the problem you are trying to solve, if it requires such generic cases where you need to track the operations, or you need to go back to the previous states, right, till the beginning, then you can think of using the stack, right? Now coming to the data operations on a stack, right, and the impact on the data operations performance you use when we use the stack data structure. Let's say adding an item at the top, right? So let's say this is a stack. If we push the one more item, basically it is very fast, right? It will just increment the top 5 and performance will be off 1. Now here I have written one new word, amortized. It basically means average time over the sequence of operations, but some, even if the individual operations takes time. Basically I was trying to highlight the dynamic array resizing case here, because uh, during the resizing it can go up to of n also, but on an average the performance is of 1 here. Again, related to this dynamic array resizing, you can check the array data structure related video into the data structure and algorithm concept series playlist. Now adding an item at the top is done, then adding an item at any place except top, right? Now if we see, if you want to push the 15 between 9 and 11, right? Now we need to pop, we need in, for such cases we need to use another stack actually. Pop and push to stack B, temporary stack we need to use. We popped and pushed 13 here, then we need to pop 11 also, then stack B contains 13 and 11. Top A is at 3, top B is at 1. Now after we pop all two elements, we can push the 15, and then again one by one from stack B we need to push to the stack A, so that it can become 5, 7, 9, 15, 11, 13, something like that, right? So in this case, the performance is O of n. What if we need to insert the element at the beginning of the stack, right? So we'll have to move all the elements to the another temporary stack and then insert and then move back again. So next is data operations on a stack, basically deleting an item at the top. Now, when we delete the item from the top, it will basically remove the top element and decrement the top pointer. So that is why the performance here is O of 1. Deleting an item at any other place except top is basically, let's say if we want to pop 11, then it is similar to the insert data operation at any other place except top, right? For that last word. So it is similar to the insert operation in between. So we need to pop the element 15 and 13 from stack and push it to some temporary stack, pop the element 11, push the 13 and 15 from the temporary stack back to the original stack, right? So because if we try to remove the element, let's say 5 here, then we'll have to do that is remove all the elements from this stack to some temporary stack and then again put this performance is O of n. And here is the number of basically the size of the stack, the number of items in the stack, right? So now searching an item. Now if you want to search 5 here, right, you'll have to check, remove each element and then pop, check. So basically it will be like you need to parse whole stack, and maybe you need to use the temporary stack also. So that is why the search operation here also is O of n, because you need to parse through all the stack elements if you want to search for, let's say, 5 in this case, right? Now access an item. If you see that if you want to access an item element at the top, it is very fast. It is a performance one, because stack library exposes the function to access the top element without removing. Now, if you want to access the element at any other place, it is O of n, because even though internally stack is implemented by array, it is not exposed to us in a library which we use in a programming languages, right? The stack libraries. So we can't access any element at any position, right? So for that, we'll have to first remove and then go to that particular index and then access. So let's say if you want to access the element at 0, which is 5, then we'll have to parse whole stack, right? And in such case, the performance is O of n, right? N is the number of elements onto the stack, right? Now we understood about the stack data structure concept based on some examples initially, and then we understood the stack implementation using array and linked list. Then we understood about the generic use cases where stack can be used, and the performance of different data operations when we use the stack data structure. Now hope you might have got a good idea about the stack data structure, and depending on all these factors, use cases and performance impact on each data operation type, whether we should use the stack data structure or not while solving the specific problem, that decision can be taken, or that will at least help you to think in the right direction. Thank you.
Hope you understood the explanation about stack data structure and different use cases, its implementation, and data operations performance using stack data structure. So that will help us to decide whether in which scenarios we can use the stack. So if you like the video, please subscribe and share. Thank you.